Hello everyone, thank you for having me here and thank you for being here. I'm excited today to present my research on artificial intelligence in macroeconomics. The first question I ask is, can an economic agent adapt its behavior with respect to environmental changes when modeled with an AI technology? In this context, it is a deep reinforcement learning algorithm. The motivation of this research is that it's important to look at learning dynamics of economic agents in a changing environment, as it may provide policy implications that are different from those based on equilibrium analysis. And the key contribution here is that through constant learning, an AI agent can adjust its policy with respect to changes in an economic structure. I want to quickly say that deep reinforcement learning algorithm, the one applied here in this research, is different from deep learning. Deep learning is applications of artificial neural networks to process an existing dataset, so it focuses on information processing. Whereas deep reinforcement learning combines both information collection and information processing. So deep learning is a component within deep reinforcement learning, and those two are not the same. First, let me introduce the environment, a stochastic optimal growth model. In a closed economy with one consumption and capital good, a representative consumer aims at maximizing its lifetime utilities, subject to per period budget constraint, consumption plus capital investment equals to this output, YT, times stochastic component, ZT. The output follows Cobb-Douglas form, and the stochastic process satisfies this equation here, where mu is the mean of log zt and rho is the autoregressive parameter. So to apply this deep reinforcement learning algorithm, I first need to convert my environment, the economic structure, in terms of components within the algorithm. So there's a state variable, and this is the total resource available to consume or invest, ZTYT. And there's the action. It's, in this environment, the proportion of the total resource that the agent wishes to consume. And the reward is represented by the period utility, log CT. And then the next state is then ZT plus 1, YT plus 1, where YT plus 1 equals to KT plus 1 to the power of alpha, and KT plus 1 is whatever is left from the total resource after the agent consumed, after the agent chose the proportion that it wants to consume. And then there's the policy function. It's the decision-making strategy of the agent. And it is approximated by an artificial neural network, parameterized by theta mu. And this theta mu is updated during learning process. And there is also an action value function, which describes the expected return given a state and an action pair. And it is also approximated by a neural network, parameterized by theta q, and it is updated during learning process as well. So for a reinforcement learning agent, it knows the current state of an environment. However, it doesn't know how reward is generated. It doesn't know what the next state is. The task that it has to do is to choose an action with the goal of finding the optimal policy. So finding the decision-making strategy that maximizes its expected return, which is approximated by this action value function here. So this algorithm involves both the information collection and information processing. First, within this information collection part, for every period, the agent observes the current state of an environment. It then chooses an action based on its policy network, plus some noise so as to explore its action space. I will focus on this in the next slide. But now just stick to this big main structure. So once the agent observes the current state, chooses an action, receives a reward, and then the state transits to the next state. And the information collection is referring to this process of saving the sequence of variables, saving this experience in its memory. And this involves state, action, reward, and next state. This information in this memory are then used as training data set for neural networks. So that's the information processing part. So for period t greater than some sample size n, meaning once the agent has accumulated enough experience or enough memory data, it then takes a sample of sample size n out of its memory and use this sample as training data set for the two neural networks. And that's how the neural networks are updated. Due to time constraint, I will not go into details on how exactly neural nets are updating itself. Right. So what do I mean by exploration earlier in terms of the information collection part? So to obtain a lot of rewards, a reinforcement learning agent must prefer actions that it has tried in the past and found to be effective in producing rewards. And this is called exploitation. But to discover such actions, the agent has to try actions that it has not selected before. So to test the unknown part of the action domain. And this is the exploration part. A reinforcement learning agent who wants to gain high rewards must balance these two components, must balance exploitation and exploration. So I designed and implemented some simulation experiments to answer my question. Recall the first question I asked: can an economic agent adapt its behaviors with respect to environmental changes? To test this learning agent's ability in adapting to changes, I want to observe their behaviors when impose a change in the stochastic process. In particular, I impose a transitory shock and a permanent change. And all experiments are done for three types of reinforcement learning agents, differing in their exploration levels. So all agents here are born with no information on how state transitions and how rewards are generated. Their policy and value functions approximated by neural networks are randomly initialized. They learn in the same environment for the same amount of periods, differing only in how they collect information, or their as represented by this exploration level. And they experience the same transitory shock and permanent change. So first, in terms of the transitory shock, this figure plots the stochastic process with a transitory shock happen at period 100. And the top panel here plots the agent's consumption behavior facing this shock. So the black vertical line here represents, well, the dotted one represents the timing of the shock. As it's shown clearly that the middle exploration agent and the high exploration agent respond to the shock swiftly, whereas the low exploration agent responded with, slowly and with a very small magnitude compared with the other two. I want to stress here that because of their difference in terms of how they collect information, they although they were living in the same environment, they were learning in the same environment, they have different past experience and memories, and which in turn leads to their different behaviors facing the same shock. On the other hand, for the low exploration agent, the blue line here, if the environment were stationary, if there were no shocks or changes happening in this environment, you would expect the low exploration guy would do the best because because the environment doesn't require the agent to constantly checking if there are changes in the environment, like an environment full of changes. So the low exploration guy will do better in this case. Whereas if there were this environment full of changes or uncertainties, you would expect a high exploration agent to do better because it's constantly checking the unknown action domain, and so they're very alert to changes in the environment. And at the bottom panel here, it plots the agent's utilities. And as expected, the middle agent who balances exploitation and exploration does the best in terms of the utility it receives. Whereas the low and high exploration agent go to the extreme and hence sacrifice their welfare. And with respect to permanent change, here I plotted the stochastic process with a permanent change happening at period 0 here. And similarly, the top panel here plots their consumption behavior, and bottom shows the utility of all three agents. And all three agents, in times of this change, shift their behaviors permanently. And again, similar to the result earlier, that the middle exploration agent, the agent who balances exploitation and exploration, does the best at earning utilities in this environment. Whereas the low exploration agent is too cautious and doesn't want to try new things, and the high exploration agent is too adventurous and always want to try new things, and hence both of them are not receiving rewards that are higher than the middle exploration agent. So combining this result with the earlier transitory shock one, so it also echoes with the permanent income hypothesis that a temporary shock leads to a temporary response of the agent, whereas a permanent change in the environment leads to a sustained shift of agents' behaviors. So to summarize, in this research, I showed a deep reinforcement learning algorithm. I combined the deep reinforcement learning algorithm with macroeconomic model, and I showed that reinforcement learning algorithms are capable to train systems to respond to unforeseen environments. Agents in this algorithm can constantly collect new information, and the information is then being processed to update their policy and value functions, and therefore they can achieve a real-time learning process. And I illustrate that learning behaviors vary with respect to agents' exploration level or how they collect information. And this also has welfare implications.